Welcome everyone to another Thursday Astrophysics seminar. We're delighted to have Professor Maya Fishbach visiting us today from CITA, the Canadian Institute for Theoretical Astrophysics in Toronto. Maya got her PhD from the University of Chicago in 2020, is that right? Working with Daniel Holtz. And I was actually telling her that we had met when I was a first-year grad student when she was visiting Daniel on sabbatical at Stanford. She wrote many interesting papers while she was there as a tension adult cosmologist, many about prospects of measuring the Hubble constant using dark sirens and standard sirens. She later took a Hubble Fellowship just slightly north to Northwestern University, where she was an Einstein Fellow there at Sierra, and then moved not too long ago to CITA, the University of Toronto. And today she'll be telling us about astrophysical lessons from LIGO-Virgo-KAGRA's black holes. So everyone please join me in welcoming Maya. And yeah.
Thank you for the introduction. So today I'll be telling you about some of the things that we've learned from these gravitational wave observations of black holes. I will also get to cosmology, I think. I know I didn't put that in my abstract, but then I decided that it would be good. It's a very brief review. We're detecting gravitational waves now. And so the gravitational waves that we're detecting are coming from systems like this, where we have these two black holes or sometimes neutron stars that are in a binary orbiting each other, and they're in a tight enough binary that the gravitational radiation is dominating the orbital evolution of the system. And here are these gravitational waves, these ripples in space-time that travel out and travel great distances across the universe, pretty much unhindered until they get to us and we detect them. And we detect them with our worldwide network of gravitational wave observatories, so consisting of the two LIGO detectors in the US, the Virgo detector in Italy, KAGRA in Japan, and then LIGO India, which I believe construction has started or is starting soon, but was recently officially approved by the Indian government and will come online 2029-ish, 2030. So pretty soon. And then as far as the observing timeline, so in their current advanced detector era, then LIGO advanced LIGO started operating and its first observing run in 2015. That was when the first detection happened in the engineering run preceding this first observing run. And then there was a second observing run, 2017-ish, where Virgo also joined at the very last month of that. And that resulted in an amazing, we didn't cause the neutron stars to merge, but it was very lucky that Virgo was online just in that last month. And we got this spectacular neutron star merger that was very well localized for us and yielded electromagnetic counterparts across the spectrum. Then we had another observing run, 03, and then 03 ended a month earlier than planned in March 2020, and we had a very long pandemic break plus commissioning. And then 04 just started last year, and we just finished a commissioning break in the middle of 04, and the detectors are now online in their engineering run. And the second half of 04 will start next week. And then we'll have 05 as well later on. And then these numbers up here just refer to the binary neutron star range. So with every observing run, the detectors are getting more and more sensitive. So the detection rate is increasing. And so that's seen here if you look at the cumulative detection rate over time. So the first observing run, we had 3 binary black holes. At the end of the second observing run, we had 10 binary black holes and 1 binary neutron star. And then we had the third observing run where you see the detection rate really shot up. And so by the end of the third observing run, we were up to like around 100 events. And then the first half of 04, we're not that much more sensitive than we were in 03, but there's still kind of like a steepening here. So this is just based on the public alerts. We haven't released any data or analyses from 04 yet beyond the low latency analyses, but we've pretty much doubled the sample in this first half of 04. Okay, and so if you look at the masses of all of the events that we've seen, so we can infer the masses of both binary components and the total mass of the system, or the remnant mass from the gravitational waveform. And so here, this plot, the y-axis here shows the masses of those different neutron stars and black holes. The neutron stars are down here. We've seen a handful of binary neutron stars and neutron star black hole systems, and then a whole bunch of these binary black hole systems where each one of these arrows represents, you have these two black holes, and then they merge to form this remnant black hole. So you can see that we have a whole bunch of black holes around the 20 to 50 solar mass range, and then also a few down at 10. And the first question that we can start to ask from the sample is just how are black holes made in our universe? So we know that one way that our universe makes black holes is through massive stellar evolution, where depending on the initial mass of the star and the initial metallicity, if you start off with stars that are around 10 solar masses or above at sufficiently low metallicities, then you end up with a black hole either by fallback, so supernova explosion, and then some stuff falls back. This is all very, very simplified, by the way, or a direct black hole, which in this recent review by Hager, Mueller, and Mendel just refers to, you have a supernova, or you have a collapse without like an actual supernova explosion. So maybe no stuff actually gets emitted and ejected. And then you can also have very interesting cases where the whole star completely explodes and doesn't leave behind any remnant. That's known as a parastability supernova. And then this whole picture is hugely uncertain. So we hope to learn something about, how these stars turn into black holes from observing this new sample of stellar mass black holes. The other thing that we want to probe is, how does the universe actually get two black holes in a binary that merge with each other within the age of the universe? So this is non-trivial, because if you have the evolution of these massive stars, they expand a lot during their lifetime. So if you just place two stars next to each other, you have to place them pretty close together if you want them to actually merge through gravitation. If you want the black holes they make to actually merge through gravitational radiation within the age of the universe. But naively, the stars would expand to fill that separation. So you kind of have to solve this problem of getting your two black holes close enough together by the time they're two black holes without having the stars merge with each other before they can end up as two black holes. So there are kind of two broad classes of solving this problem and getting two black holes that merge within the age of the universe. The first is through isolated binary evolution, which just refers to any situation where you start off with two stars that start off in a binary, they live their lives together, they one by one die and become black holes, and then you have the two black holes that are somehow close enough together that they can merge within a Hubble time. So for example, you can have common envelope evolution over here, where the envelope from this star before it goes supernova encompasses both stars, both the star and the black hole, and then some orbital energy and angular momentum gets dumped into that envelope, and leaves the two remaining. Then after the common envelope is ejected, your two objects are close enough together here that by the time they're two black holes, they can actually merge within the age of the universe. The other class of formation scenarios that we consider are dynamical assembly, which I talked about earlier today at the dynamics meeting. And this refers to anytime you just have a bunch of black holes and through dynamical interactions, they assemble into a binary that's tight enough to assemble with. And then we can also learn broadly about the universe with these gravitational wave signals, because these binary black holes are merging inside galaxies, and we can learn something about possibly the large-scale structure and the cosmic expansion history from these signals. So I'll talk a bit about that as well later. So we can learn about everything from stars to galaxies and cosmology with gravitational wave sources. But we have to start with the actual systems that we're observing. So the gravitational wave signal carries information primarily about the masses of the two black holes. So we can learn how big is each black hole. There's also some information about the spins of the two black holes. So each black hole might be spinning, and that carries information about the spin magnitude as well as the spin orientation. So how is each black hole oriented with respect to the orbital angular momentum axis? And then there's also some information in the gravitational wave signal from its amplitude. We can infer how far away the merger happened. So that's the luminosity distance. And then in the first part of my talk, I'm going to assume that we know cosmology perfectly. And so I'll use luminosity distance and redshift interchangeably. But in reality, the gravitational wave signal does not carry information about the redshift, or the gravitational waves do get redshift, but the redshift is degenerate with the mass. So we really just get the luminosity distance. And then we also have some information if we have multiple detectors that are online about where in the sky the signal happened. Okay, so in order to actually learn about astrophysics, we have to look at all of our events collectively, and instead of analyzing them one by one, analyze them as a population. So we take our individual event parameters, like what are the masses of each black hole, and introduce some population model that describes the distributions of masses, for example, across multiple events. So one example, which is the first thing that we did, is just fit a power law to the black hole masses. So here you have a power law with maybe some minimum mass, a maximum mass, and then your power law slope. And that just describes the rate of merging binary black holes as a function of the primary mass of the black hole. To do this, we have to take into account the measurement uncertainty of the individual events. So the fact that we don't perfectly measure a black hole to be 10 solar masses, for example, but there's some uncertainty around that. And we also have to take into account selection effects. You might note here that this distribution, has a lot of support at 10 solar masses, but our detected distribution, we have a lot of 30 solar mass black holes. So we correct for these selection effects. And this is all done within a hierarchical Bayesian framework. One thing to note is that it's very tempting to just fit the detected distribution directly rather than this underlying astrophysical one. But you shouldn't do this because there are correlations between the measurement uncertainty and the selection effects. So Reed Essick and I recently explored that in a paper. What kind of biases you might get if you don't use the correct likelihood. So you have the correct likelihood, use it. So this is what I was talking about before with the selection effects. So we do have to worry about selection effects with all this analysis. The major selection effect is as a function of mass. So if you look at our sensitive volume as a function of the total mass of a black hole system, then as you increase the total mass, these different colored lines are just different mass ratios, then we're probing a much bigger sensitive volume of the universe to that type of signal, because more massive gravitational wave sources are, the gravitational waves they emit are louder, so we can see them to greater distances. So we have to take these selection effects into account, but we're extremely lucky in gravitational wave astronomy because we understand our selection effects really well, because we know DR. So we know what the gravitational wave signal from a given source would look like, even if we haven't observed that source. And so that's something that is quite unique, which is, I think, kind of one really powerful aspect of gravitational wave astronomy is our selection effects. Okay, now for the next half hour or so, I hope to tell you about some things that we've learned from the gravitational wave sample for astrophysics and cosmology. So the first one I'll talk about is formation environments. Can we distinguish whether binary black holes are made from isolated binary evolution or from dynamical assembly in clusters? Then I'll hope to tell you a bit about the merger history. So can we actually infer how long ago black holes were made? And then I'll get to some cosmography. So what can we learn about the expansion history of the universe? Okay, so starting off with formation environments. So showed this picture before. Basically, can we learn something about whether our black holes formed through isolated binary evolution, or were they dynamically assembled in a cluster? The main thing to note is that if they've evolved from dynamical assembly in a dense cluster, then they'll have a specific signature in the spin distribution. And so we can learn about the spins of gravitational wave sources primarily through this one parameter, which is the effective in-spiral spin. So this effective in-spiral spin, chi effective, is the mass-weighted spin along the orbital angular momentum axis. So if you have your two black holes in a binary, the orbital angular momentum here is L, then they could have some, the spins are tilted maybe with respect to the orbital angular momentum. That's theta 1 and theta 2. And so you take the spin of each black hole projected along this orbital angular momentum, and then you just take the mass weighted average of that. So basically, if both black holes have very small tilts, less than 90 degrees, chi effective will always be positive. If the spin tilts are completely random and so flat in cosine theta, then half the time chi effective will be positive and half the time it will be negative. So we can use this fact to distinguish between, so if we have negative chi effective, we know that some spin tilts were larger than 90 degrees. That's easier to accomplish via dynamical assembly than if you just have isolated binary evolution, because the spins of the stars will tend to be aligned with each other. And then so it's harder to get large spin tilts through isolated binary evolution. And then if you have isotropically oriented spins, that's what you expect from dynamical assembly in, for example, globular clusters. So that would imply a chi-effective distribution that is centered at 0. And yeah.
So how should I think about this with respect to the distribution of masses of the black hole? Because I can imagine that if you have some population of very massive black holes, that are your M1 here or something, that these statistics could change. Do we have an understanding about the distribution of masses, or is that not the right way to think of it?
You mean because like M1 and M2 directly affect high effective? Yeah, so you can also write this just in terms of the mass ratio. So this is like the total mass here is invariant. The only thing that affects high effective is the mass ratio if you just like divide both of them by M1 plus M2.
So then there's the assumption that the theta 1 and theta 2 are independent and not associated with the masses as the contributing matrix.
Yeah, that's a good way of putting it. There's the assumption here in this dynamical assembly case, then there's the assumption that both spins are drawn independently. And yeah, there's no correlation. But yes, I won't talk about this at all, but there is evidence that the high effective distribution does actually vary with mass ratio, like on a population level. There's a correlation between high effective and the mass ratio. And that could imply that that the spins are not, the spins are not independently distributed, like spin 1 and spin 2. And that perhaps the way that the correlation goes is kind of weird because it would imply, if you interpret it in this way, that the spin of the primary tends to be spinning more along the orbital angular momentum than the secondary spin is relatively smaller when you project it along the orbital angular momentum, which is, not what we typically think would be where we think like this, that's the secondary would be tidally spun up, for example. I know that there was like work here by Matthias and others about that. Yeah, so that's kind of weird, but for now, I'm going to just like neglect any other correlations. Yeah, so again, neglecting these correlations, if we just take the effective spins, high effective of our binary black hole sample, and again, take into account these measurement uncertainties and selection effects, which for high effective do push you towards detecting larger positive high effective compared to negative high effective. So we factor that out and we just consider here the cumulative distribution in terms of high effective, and these two different colors are just different models, like parametrized models, but it doesn't make a big difference here. Basically, when we look at this distribution, we find that the majority of black hole spins are positive. So if you look at the 50th percentile, it is above 0. So that leads us to infer that spin orientations are not isotropic, because otherwise, 50% of them would be above 0 and 50% of them would be below 0. But there is evidence on a population level that some black holes have tilts larger than 90 degrees, and that there is, maybe a very, very small, but it seems to be a non-zero fraction of systems do have high effective smaller than 0. So from that, it seems like we do have some contribution from dynamical environments like globular clusters, but perhaps not all of our mergers come from clusters, because we do have a preference on a population level for positive high effective. What we can do is to actually measure what this fraction of negative high effective systems is as a function of redshift, and use that to infer what the contribution from globular clusters is as a function of redshift. So what I'm showing here is the total rate of mergers as a function of redshift is shown here in the orange unfilled bands. And then if I look at the fraction of systems that have high effective smaller than 0, multiply that by 2 to get the fraction that are consistent with having isotropic spins, then I get the blue. So the blue is always less than the orange, but also the error bars are really big because it's hard to measure the chi-effective distribution, especially if we allow redshift like this. Anyway, the blue here gives us basically an upper limit on the merger rate of that's coming from globular clusters. But I'm just going to, let's just assume that this, upper limit of black hole binaries that have isotropic spin tilts is actually the same thing as the rate of mergers originating inside specifically globular clusters. So one type of dynamical assembly environment.
Because you mentioned
Yeah.
that you have this evidence at a population level. Remind us how many because there are specific systems that we see chi-effective positive and no problem.
Yes.
But are there now some systems which chi-effective is clearly negative on an individual level, or it's just more than you count them?
Yes, that is a great question. And so there are no systems that have chi-effective smaller than 0 with more than like 90-ish. There's a couple that it's like 90% credibility chi-effective is negative. But we don't have, so yeah, we definitely have clear systems where chi-effective is positive, which here we can, it's hard to see, but chi-effective does extend more to the positive direction. So like we have systems where chi-effective is probably like 0.4 and at least 0.2. We don't have any such systems individually on the negative end, but we probably wouldn't expect to just with normal error bars. If chi-effective is really negative 0.1, it would be very hard to rule out 0. So you're right, you can construct a population model where the support for chi-effective less than 0 goes away. Like you can just have a sharp cutoff at 0, and like that would be consistent with the data. But it seems that there's enough individual events that kind of have a preference for chi-effective smaller than 0 that under like our usual population models, there is support for negative chi-effective.
There are selection effects in this as well, presumably, which have all been accounted for.
Yeah, the selection effects have been accounted for, in that it's in the detected sample, we expect to have more positive chi-effect. Even if the chi-effective distribution was symmetric, the detection biases would yield like more positive chi-effective because there's more angular momentum for the system to shed. And so the gravitational waves have to carry more away. So they're louder.
So in practice, by the time you're talking about 0.1 of chi-effective, it's not a
Yes.
big selection.
It's not, yeah, it's like a factor of like a few over the entire range, like -1 to 1. So in this region close to 0, it's not a big effect at all.
I mean, another way of thinking about it is now you are demanding that these two channels have similar rates, right? So you are fitting better maybe the tail of the chi-effective negative, but somehow these two channels happen to have the same rate, which I don't know why. It's just from some outcomes rate, so you can pick there's only one dominant channel. That I forget about the negative. I could take that one. Instead of having the globular clusters and having almost, one factor of a few less.
Yeah, I mean,
Given
even
that if
here,
you start from the beginning, all of these rates can have orders of magnitude, right? From the theory side, you can allow anything. So
The theory said they all exactly agree with the LIGO, right?
as the anyway.
yeah. Yeah, I agree with that. I didn't hear like it's still an order of magnitude uncertain when you when you try to count like the fraction that's negative chi-effective. But even I would actually like if we can really rule out any negative chi-effective systems, I'd be happier with that, because I think if we push this upper limit down a lot, then we learn a lot about globular clusters. Like, you have to do some weird things to prevent globular clusters from merging any binary black holes. I mean, maybe not that weird. Like, you can just assign big ticks to all black holes, and then you wouldn't have any black holes in clusters. But we also see black holes in globular clusters, so I don't know. Yeah, okay, so all of what I will tell you are just like things that you can learn about globular clusters, which you could also learn if you push that limit on the merger rate down to close to 0. But okay, so binary black hole mergers can probe globular clusters, and so the main way is that we can translate the merger rate that we measure in clusters to constraints on the population of globular clusters. And so the main example is that the number of binary black hole mergers that are produced by a given cluster scales very strongly with the mass of the cluster. So here it's showing the mass of the cluster in units of 10 to the 5th solar masses. And the different lines here are the different virial radius of the clusters at birth. And so you can see that the densest, smallest radius, biggest, most massive clusters have the highest number of mergers that they produce. And so the rate of binary black hole mergers depends strongly on the properties of the globular clusters. And so this figure is taken from this CMC catalog paper led by Kyle Kramer. And I'll be using this CMC. So CMC is cluster Monte Carlo. That's the Monte Carlo code that they use to evolve these black hole populations in the cluster. And so I'll be using these predictions to then try to turn, okay, like, what's the number of binary black hole mergers in the universe? Can we turn that into constraints on, for example, the globular cluster mass distribution?
Are we there as in parsecs?
Yes, this is in parsecs.
And the lines are just straight line fits to the data from CMC?
Yeah, they just fit these lines here because also they tried to extrapolate to very high mass clusters that they didn't simulate as many of, like up here. But yeah, I won't be using those lines.
A cluster with 10 to the, sorry, could you just go back? A cluster with 10 to the 6 solar masses and a virial radius of half a parsec. Are there any globular clusters like that?
Not today.
Okay.
Not that we see. Yeah, I guess reasonably, I think like the one parsec is probably closest to the initial distribution, but
And sorry, just coming back to this, and the formation of black holes in CMC is done sort of self-consistently, right? There are some prescriptions. It's not like there is some fraction of black holes that are seeded, so binary black holes that are seeded.
yeah. Right, so there's some initial I don't know about self-consistently, but there's an initial population of stars that's distributed according to a density profile in the cluster, and there's an initial mass function, initial binary fraction, which is probably too low to be realistic. And so there's like an initial stellar population that is then evolved with rapid population synthesis and like gives you a black hole population.
The spins are like fed by hand.
Yes, the spins are put in by hand and not even tracked in the simulation, other than like, I think for all of this, the assumption is that black holes are born with zero spins.
So if I look at some of the points on this plot that are at the same place on the x-axis, but have the same color. So RV of 4, the mass total of about 5.1. There are lots of there are 5 or 6 different points there, which are presumably from different realizations of the cluster.
So, yeah, so in addition to different, so in this catalog, there's a different mass and radius of the clusters, but there's also like a different position in the galaxy and initial metallicities. So I think there's like, there should be 9 different points for each of those.
I would assume this result would have a very strong sensitivity to the assumed King distribution at the birth of the black holes.
Yeah.
So have CMC been used to try to replicate these 3 detected black holes in one of the globular clusters?
Yeah.
Just to try to get these numbers more or less straight, given the selection effects and so on.
Yes, I think from talking to Carl Rodriguez, they cannot, with the default settings, they cannot get such low mass black holes inside those clusters because they assume that the kicks of those the natal kicks of those black holes would have been too large.
Should we be replaced then?
Well, yeah, I guess you can. I don't know if you should believe this. I think you can believe, if anything, the number of binary black hole mergers would then be too large. I mean, I think that there are a lot of uncertainties about like what the natal kicks of black holes are, like what the initial distribution of stars is in any environment. I would think that the main effects here are the globular clusters themselves, like the initial conditions of the globular clusters, rather than the uncertain like distribution of stars and the
Yeah, I guess the
stellar
scalings
physics.
still survive, these RE or these the mass.
Yeah,
This
and I think I purposefully, so I won't be using any information about the masses of the black holes to do this comparison, because I think like thinking about what masses of black holes are retained in clusters, or even like what the mass distribution of black holes in different environments is hugely uncertain. I think like the number of black holes and how that scales with the mass of the cluster and the radius of the cluster is more robust, just through dynamics.
Yeah, just to give an idea, I think I completely agree with that statement. That's what we were saying this morning. CMC, for instance, if you have 3 bodies coming together and you think they're going to form a binary, it automatically pairs together the 2 heaviest ones and has some probability of forming a binary. And then the people in Fred Razio's group a few weeks ago showed that when you actually do proper n-body simulations, it's the 2 lightest ones that actually form a binary. So a lot of these prescriptions are not calibrated on anything.
Yeah. Okay, so basically, again, as a reminder, we're using this rate of binary black hole, the blue, the rate of binary black hole mergers from clusters as a function of redshift, between redshift 0 and redshift 1, because that's what we can probe right now with our gravitational wave sources. We can use that to place some constraints on the properties of the clusters. So different cluster mass distributions will lead to a different rate of binary black hole mergers. And so for example, we can constrain what the mass distribution of clusters is. It's consistent with what is typically assumed, which is a Schechter function with like a slope of -2 up until some knee here and then an exponential decay. We can also learn about the overall formation rate of globular clusters as a function of redshift. So here, plotting the number density or the mass density of globular clusters as a function of redshift, all the way up to redshift 20. And for comparison is the star formation rate, and then this is the inferred cluster formation rate. You might be like very confused. How am I learning anything about the formation rate of clusters at redshift 20 if I'm only learning about if I'm only measuring the merger rate up to redshift 1? And you're right, this is all up here, it's all like dominated by my choice of prior, but we actually are learning about the cluster formation rate up to around redshift 5 or so. And that's because of the very long delays that black hole mergers experience between the birth of the stars in the cluster to the merger of the black hole.
Does this modeling account for the destruction of globular clusters?
So it doesn't assume anything about the disruption of globular clusters, but if you integrate this merger rate and ask what would be the density of globular clusters today. Okay, so first I'll say a piece about redshift 3, and yeah, so if you do that integral, then you infer that the formation rate is around 20 times higher than the present day density of survived clusters, which would mean that there is high cluster evaporation, or that this is an overestimate of that we've overestimated the rate from clusters, and so the cluster rate is not actually this.
Your Schechter function seems to have a characteristic mass of around 10 to the 7th solar masses. Clusters like that don't evaporate typically, so where are all those clusters today?
Yeah, so this is right, the only clusters that are in the catalog that I've used for the simulation are like these bins here. So this is assuming that the rate density of clusters is very high, like at these low masses. So that's what I'm plotting here is like down to 10 to the 4 in cluster masses. So yeah, I guess this is the cluster evaporation factor, which is kind of what this like 20 here is on the high side of what is typically predicted. But it's, yeah, so again, I think probably this rate that I've said here is from clusters is really higher than the rate of binary black hole mergers that originate from clusters. I think that's part of it, but it's hard like with this, because of the fact that like we've extrapolated what the rate should be at high masses and at low masses. It's hard to like turn this number into a cluster mass specific number. So I'm not sure if this number would imply that like it would be inconsistent with the fact that we don't see these clusters.
Well, it's just that I don't know of any mechanism for destroying clusters above 10 to the 6 solar masses.
Yeah, right. So they don't necessarily have to be destroyed. I mean, they could just now be like 10 to the 5 solar mass clusters.
Well, I don't know of any mechanism to convert 10 to the 7 solar mass clusters into 10 to the 5 solar mass clusters.
Does your constraints in number of clusters formed or the mass, stellar mass in clusters of any mass?
Yeah, so it's a little bit together in that we're constraining the number of clusters formed per mass in this range, but then we're extrapolating out to higher masses. So we're constraining the mass density of clusters, but it's somewhat extrapolated. And it's hard to, yeah, so it's a little bit hard to disentangle whether we're constraining the number density or the mass density of clusters. And especially when you combine it into like this one number, like evaporation fraction or something, yeah, that's kind of what I was trying to say to Scott, is that it's hard to distinguish, is that coming from a specific mass range, or is that like a number density or mass density? Yeah.
How are you using the actual masses of the black holes in LIGO? Are you assuming that the globular clusters is the shape of the mass function the free, or how?
So for this analysis, there's no information coming from the shape of the mass function.
But one must is this rate of mergers black holes computed to match to the globular? I'm confused by it.
So
The rate.
Yeah, for this rate that we measure, we have to like simultaneously model the mass distribution of binary black holes because it's degenerate. So this is simultaneously inferred with the mass distribution of binary black holes, but that's mass distribution does not go into like this, for example. We're not.
This is kind of assuming that that shape, whatever it is that you are measuring, is the one that globular clusters produce.
Yes. Yeah, okay. So maybe I'll move on for now. Yeah, so, so one aspect of this is like, we've used the prediction of the delay times, like how long does it take from cluster formation to binary black hole merger to reconstruct this curve, for example, but you can use that more generally, because like taking a step back, the binary black hole mergers that we observe are probing star formation history at much earlier times because, there was the Big Bang and then stars formed. And this graphic is for the binary star case. And then you had very shortly after the stars were born, the black holes were born. These are massive stars, so they only lived for like 10 million years. But then there can be a very long gravitational wave in spiral until we actually see the merger of the black hole now between like redshift 0 and redshift 1. So there's some delay time, which is dominated by the gravitational wave in spiral between the formation of the stars, whether they're born in a cluster or in the field, and the merger of the black hole. And so one thing we can do is, if we know what the progenitor formation rate is, then we can actually measure the delay time distribution. So this plot is showing a slightly outdated measurement of the binary black hole merger rate from redshift 0, or a look back time of 0, and redshift 1, or around 8 billion years ago, just normalized to the merger rate today. Because just from observing the shape of this distribution, does the merger rate increase as we look back in time, or is it like kind of flat or decrease? We can learn something about the delay time distribution. So in orange here is the star formation rate. And so if we assume that the progenitors of these binary black hole mergers just follow the star formation rate from observing the shape of the merger rate as a function of redshift, we can learn something about other lines here are what the merger rate would be if the progenitors followed the star formation rate with delay time distribution. Here, assuming a flat and log delay time distribution and just varying the minimum delay time. So because the merger rate increases with increasing redshift, we can rule out the longest delay time distributions because they are inconsistent with this shape. So I'm going to skip this slide, but we can compare that against theoretical predictions for the delay time distribution, for example. So switching gears and talking about isolated binary evolution, there are two kind of ways of transferring mass in a binary system that can lead you to a binary black hole merger. One is through this common envelope channel, where you have this magical common envelope that tightens the orbit very quickly. And so you can have very short delay times. And one is without common envelope. So the mass transfer is only stable. And so that leads to a much shallower delay time distribution. And so in terms of like these, there's still a lot of different models, model variations within these. So you can have like a bunch of different delay time distributions, but on average with common envelope, your delay time distribution is roughly flat and log, or time delay to the -1, whereas for stable mass transfer, it's much shallower. So around time delay to the -3.35. And so, okay, so, you know, we
Does the
can,
normalization mean something? Or
yeah, the normalization here is like the overall rate, basically. So common envelope also just leads to more mergers in according to this model. Basically, like it pushes you to more things that actually merge within the age of the universe, as opposed to time. The stable mass transfer, where like you'd have a bunch of systems out here that don't merge within the age of the universe. Yeah, so we can, so if we like assume progenitors follow star formation rate, we can measure the delay time distribution and maybe distinguish between different astrophysical processes that are responsible for getting these black holes to merge. Alternatively, if we assume a delay time distribution, so here on, I should say the common envelope channel is close to this time delay to the -1, but also if you add these together, because the common envelope dominates, then you get a time delay to the -1 distribution for like everything from the field. And according to these models, which Lika Van Son ran according to like the COMPASS binary population synthesis code. So if we assume that delay time distribution, like if we assume that, you know, theory is perfect, the delay time distribution follows time delay to the -1, then we can take our binary black hole merger rate and like propagate that backwards with our time delay distribution, and then infer what the progenitor formation rate should be to be consistent with that merger rate and that time delay distribution. And so that's what is shown here. In green is the inferred progenitor formation rate as a function of redshift. And then these two lines here are different star formation rate measurements. So we can like actually compare our inferred progenitor formation rate to the star formation rate. In this case, we infer that the progenitor formation rate probably peaked at higher redshift than the star formation rate. So again, now we're assuming that theory is perfect, and we know the delay time distribution, and also that we know the star formation rate, and we can divide those two things. So again, like big assumptions here, and focusing on this green line, which corresponds to the green line. There, we can yield. So what's the number of binary black hole mergers per unit of stellar mass as a function of redshift? And this is interesting because if we also have a prediction for what that yield should be as a function of metallicity, we can turn that measurement into the average metallicity as a function of the formation redshift. So again, focusing on green here for like our delay time distribution, we can actually have this measurement, which again has taken a lot of assumptions into account, but it's a measurement of, you know, what's the metallicity distribution is as a function of redshift. And like we can compare it to these other measurements shown in blue, yellow, and gray here. So this is.
Why are there three IE? What is that about? So,
Yeah, sorry, I did this very quickly, but basically that's for different assumptions. So each one of these has 3 lines because those are different assumptions of what this curve looks like, because this is uncertain from population synthesis. So that like the high yield case is if the yield is very high, and then like the low yield case and the medium yield case. And then the different panels are different assumptions for the delay time distribution. Yeah, but anyway, it's a kind of, at least it's a kind of self-consistency check. Like if you believe your population synthesis model and your star formation rate model, like do you get something for the metallicity distribution that is also kind of reasonable? Okay, I ran out of time, so I guess I won't say anything about cosmology. But I don't know. I guess one thing I will say about cosmology is that another kind of application of this like population analysis is that cosmological parameters are population level parameters. What we measure, everything I've told you that we measure has assumed fixed cosmology, but we could elevate those cosmological parameters to population parameters, just like the parameters describing the shape of the mass distribution or the merger rate as a function of redshift, and simultaneously infer those parameters. So the most information is going to come from our mass distribution, because if there's some source frame mass distribution and then a redshift distance relation, what we actually measure in our detectors is the detector frame masses, which are the source frame masses times 1 plus redshift. And so if we get data that's detector frame masses as a function of distance, we can hope to simultaneously measure the redshift distance relation in the source frame mass distribution. But exactly how you do that is tricky, because the source frame mass distribution may not actually be fixed as a function of distance or as a function of redshift. There could be some astrophysical evolution. And so doing that properly, I think, still requires more work. But because our statistical uncertainties are so big at this point, we can ignore the systematic uncertainties for now. And so we can get if we include binary black hole mass information from our latest catalog, I skipped telling you about this, but 170817 gives us a measurement of the Hubble constant. That's the binary neutron star merger, because it has an electromagnetic counterpart. So we know the redshift perfectly for that one. And then if we add in that binary black hole mass information, just focus on the orange line, which is like our best mass distribution model out of these so far, then that does add some information a little bit. And so we get like a slightly better measurement of the Hubble constant. But yes, with that, I will conclude. So hopefully I've convinced you that there's a lot to learn from gravitational wave populations, evidently more than I can say in this talk. So one thing we can learn is just how are these sources made. That relates to supernova physics, like parent stability physics, mass gap between neutron stars and black holes, but also about natal spins of these sources. And then like the mass ratio distribution can tell us about how they actually find each other and pair together. And then where and when do black holes and neutron stars merge? So within the context of cosmic time and other things that are evolving in the universe, like stars and galaxies and the metallicity of stars, does their progenitor formation rate follow the star formation rate, whether that's the low metallicity star formation rate or the star formation rate inside globular clusters? And then what are the host galaxies? Gravitational wave sources is also tied into this. And then moving even broader and thinking about the cosmological implications. So maybe we'll have something to say about the Hubble constant, and then also like probing dark energy, both through the background expansion of the universe, but also basically any theory of dark energy that's not just a cosmological constant is really like a modification to gravity, which could affect the propagation of gravitational waves through space-time. So that's another way in looking for deviations from GR and how gravitational waves propagate, that we can say something about dark energy. And also, we might have something to say about large scale structure and also gravitational lensing of gravitational waves. That will all become more promising once we have hundreds and thousands and millions of gravitational wave sources. Yeah, so with that, I will stop talking.
Thank you. Let's take a break. We can take a few questions. Are there any?
So what is a sort of number of binary neutron stars that are now considered to be real from LIGO data?
Two.
Two only. Okay. So at which point, how many of those do you need to start meaningfully compare them with the population of double neutron stars in the galaxy and seeing whether they're consistent or not?
Yeah, so we have two binary neutron stars and a handful of neutron star black hole
But
systems.
those we don't know in the galaxy, so I'm just talking about binary neutron stars.
Oh, yeah, so just talking about binary neutron stars, we've already ruled out the galactic distribution of binary neutron stars because our second binary neutron star is two pretty high mass neutron stars, like 1.6 solar masses and 1.6
Oh, that's just
solar masses.
based on masses, but what about the rates?
Oh, the rates. There are very big uncertainties in predictions for the rates. So it depends. So our rate right now for binary neutron stars is like a few hundred mergers per cubic gigaparsec per year. That is, yeah, it's basically back to where we expected it to be before 170817 tricked us into thinking it was much higher. So it's like consistent with what we see in the galaxy, with like huge uncertainties around our process inference of binary neutron star merger rate, and like also pretty big uncertainties on like the rate that we would have inferred from short gamma ray bursts, but I think it's all pretty consistent.
Thanks.
So about the first part of your talk, you were using this negative dielectric population. But then, I mean, I guess even in some hydro simulations, like the isolated ones can also have some tail for the negative case. I guess, like, is that tail very small? So you can assign these negative things to all globular clusters? Or?
Well, our data is telling us that tail is probably small. No, I think, yeah, I think it really is an upper limit on the rate from clusters. I think we don't know anything about the spins from binary stellar evolution. I think that I think under the assumption that the spin of the black hole comes from the rotation of the star, it is hard to get large misalignments just through supernova kicks, because then you tend to like break up your binaries anyway. But yeah, we like to make the assumption that the spin of the black hole comes from the rotation of the star, because at least that gives us something to start off with. But that, like, we don't know that to be true. So yeah, like the supernova can, and yeah, basically we don't know where the spins of the black holes come from. So if they come from something that's not the stellar rotation, then yeah, they could be misaligned by more than 90 degrees. But I think even in that case, we've learned something from the fact that the spins are not random.
I can ask one. So you mentioned this notion of modified gravitational wave propagation just sort of at the end.
Yeah.
But I know that a lot of work has been done basically just looking at the differences in the speed of gravitational waves versus
Yes.
the speed of light. Are there other probes of modified propagation that you can use to constrain dark energy?
Yeah, so we know that the speed of gravitational waves is the same as the speed of light, from the multi-messenger detection. So I think that like, I mean, it's the same within like 10 to the minus large number, like 30, I don't know. So they're basically the same. But there is a class of theory, or yeah, there's a bunch of different ideas that, the basically gravitational waves experience some kind of friction term. So the amplitude of the gravitational waves is less than what we would expect for like a source at that same distance under GR. So we can basically see if the distance that we infer from gravitational waves is actually like the luminosity distance of that source. And then yeah. What was I gonna say? I don't remember.
All right, and we can have break for lunch. I'll just also say we still have spots for dinner, so sign up by the end of like 1:30 p.m. maybe, just so I can actually make the reservation on time if you'd like to join us. And let's thank Maya again for the great talk.